Hello, everyone, and welcome back to AWS What's Next, my favorite launch-oriented show on Twitch, but no one needs to know that we're the only one. We're your hosts, Nick and Rob. We are here with a very special episode of What's Next. We made it to the 10-episode mark. It has been quite the journey so far, right, Rob?
Absolutely. Yeah, this is like we always say, this is a fantastic episode. I'm realizing that every episode is special in its own way. And it's very, very difficult. We're not doing apples to apples comparisons between episodes anymore. I think we should just deprecate that. Right. Every episode we have a unique launch. We have subject matter experts. We're going to dive deep with them, and you're going to get to ask them questions. So we think this is a unique format to learn about everything that's happening across AWS.
Yeah, exactly. And we've had this running joke that we've got a very special episode lined up, and every episode has been special because in the world of launches at AWS, it is never a boring time, right? We've seen launches across every facet of technology, I guess you could say, so far, and that trend does not cease to continue with today's episode. I know we typically sometimes try to keep people guessing with what our launches are, but we've sort of done away with that. We're throwing it right in the title. But if you're just joining in, you haven't gotten to take a glimpse at that, we're going to be joined by two teams today to do some deep dives on very, very recent launches. Those are going to be the Amazon Braket team, talking about quantum computing and the AWS service in Braket that will enable customers to work with that and run their experiments. We'll get into that in just a moment. But what's the second launch we're going to talk about today?
Yeah, the second launch we have is AWS RoboMaker WorldForge. This is a suite of tools that you're going to be able to use to accelerate the process that it takes to launch different IoT devices, robots, that kind of thing. But I want to say one other thing, Nick. Everybody watching in Twitch, it's Friday. It's been a long week, probably for you, definitely for me. So I suggest that we start playing a drinking game on What's Next. Every time Nick says undifferentiated heavy lifting, you have to take a shot, or at least give us some noise in chat, because he says this word a lot and I like to give him crap about it. So watch out for him. He loves this word. He's going to say it. I guarantee you he can't control himself.
I'm a creature of habit. What can I say, right? I'm out of coffee. I've got the mug still, out of coffee, but we've got water. We stay hydrated, and you need a lot of hydration to be able to say that phrase as many times as I do. So rip on me all you want, but let's at least see it in chat. But that's a great call out Rob made. Again, live show. We're here on Twitch. We're here on LinkedIn Live. We're watching the chat. One of the most fun parts about this show for us is that we get to take your comments, your questions, and your ideas for our game that we run at the end of the show and incorporate them in. If there's a service that you have questions about that we'll show in a little bit, please get those in. We're going to forward those along. And we want you to feel like you're part of the broadcast, right? We're not talking at you. We're having a conversation and trying to be able to help facilitate those conversations with the service teams that do some really amazing work and build these products and services. So yeah, I won't say it, but Rob wrote it in chat. It's the three-word phrase.
Hey, just letting you know.
It's like staring me in the face, right? But regardless, before we go into the demo sessions, there are so many launches here at AWS. If we were to do the level of demoing that we do with these services for all launches, I think Rob and I would be quite literally chained to our desks here, and we would just never go off the air, right? We'd just be a 24/7 newsroom. While we wish we could do that, that's impossible for some logistical and operational reasons. So we will have another segment here at the front where we like to talk about some of the other launches that we won't have on the broadcast today, but still we think are quite interesting to many of our customers. So quick run of show again. We're going to go through some of these launches that will not be joining us today, but are valuable nonetheless. We have some very exciting deep dive sessions. We've got two of those lined up. Then we're going to play a little game. We're going to string them together and have a little bit of fun at the end. It's Friday. We're all ready for the weekend. But nevertheless, we have some launches to cover. So, Rob, do we want to get into the first segment here?
Absolutely. Yeah, take it away.
Awesome. Well, we've got, I think, 5 that we're going to talk about today. First of which is actually a new batch of AWS heroes. So we've spoken about this a bit before. There have been some iterations to sort of these community programs over the years. We had the Community Builders program that we spoke about sort of at length on a prior broadcast, so I won't bore you. But the AWS heroes are folks and community members that are doing amazing work with AWS, writing code samples, helping to run and be leaders in their community, and truly being stewards of of the community in every sense of the word. So I'm going to be ridiculous and name each of them at least by first name to the best of my ability really quickly. These heroes are located all around the world. Welcome to the program. We're happy to have you, and we're happy to be able to highlight you for the great work that you do. Those names really quickly: Angela from Denmark, Avi from Israel, Hirokazu from Japan, Ian from Australia, Jacopo from Italy, Jeremiah from France, Kataya from Thailand, Konstantinos from Greece, Kyle from Taiwan, Linghui from China, Luca from Italy, Mathieu from France, Mike from Australia, Noah from the US, Olakelan from Germany, Peter from Australia, Ruofei from China, Sheen from the UK, Sridevi from India, Stefan from Portugal, and Tom from the US. So, when I say global, I hope, it would have been really cool to have a graphic that was like a little globe, and every time I said one, it would have like lit up, right? But it's I've only got so many hands, can't run that much production quite yet. But thank you for all the work that you do. Welcome. We're excited to have you as part of the Heroes program.
Yeah, congratulations, everybody. This is a very, very important program. I've said this before, and I truly believe it. It's one of the things that makes AWS special is the community, the ability to connect with other people who are passionate about cloud infrastructure, about different services that help you get stuff done faster. And that's what really makes it special, right? If you go to any one of our first-party events, you're able to connect with other people who are passionate about the same things that you are, who have the technical expertise to help you answer deep questions and save a lot of time and money. So I can't thank the Hero community enough. They are true experts. I mean, a great example is Alex Debris, who has written a book on DynamoDB and is considered one of the foremost experts on DynamoDB. I mean, to the extent that we at AWS, a lot of service teams that use DynamoDB reach out to Alex and have design discussions with him. Just that's how good he is, right? And we have lots and lots of really talented folks like that across a whole range of services. And as Nick mentioned, distributed all over the world. So really warm welcome to all those new heroes. I really look forward to meeting all of you.
Yeah. Wonderful. Well, one of 5, we've got 4 other launches to talk about here before we get into the demos, and we don't want to keep the folks waiting. So Rob, I think you're taking number 2 or number 1 here, I guess, if we're zero indexing.
Yeah, zero indexing all the way. So we have a pretty interesting announcement for Amazon FSX for Lustre. And for those of you who aren't familiar with this service, Amazon FSX for Lustre is a distributed file system, basically. It can be backed by a different set of options for storage. But historically, it's been backed by SSD because a lot of workloads out there have requirements for really low latency seek times, and that's where SSDs excel. But the thing is, I mean, if you're on the market for SSDs or traditional hard drives, you know that there's kind of like a price performance trade-off, right? And what we wanted to do was provide customers that option for Amazon FSX for Lustre to choose the storage medium. And so now, generally available across all regions where Amazon FSX for Lustre is available, you can now choose to back that with HDDs instead of SSDs. And this can lead to up to 80% savings for your workloads that don't require, sub-millisecond random seek time. And you might be wondering, okay, well, but is it a lot slower? And actually, what's really cool is that you can provision an SSD cache in front of your HDD tier, and you can kind of get the best of both worlds that way. And the final thing is that, of course, the HD-backed solution also has all of the same capabilities and features that you've come to know and love with Amazon FSX for Lustre, such as daily backups and linking to a file system S3. So really big announcement here for those who really want to optimize their costs and are running workloads on top of FSX for Lustre. FSX, try saying that 10 times fast.
Yeah, I mean, this is super exciting for all the reasons that you mentioned. I think broadly this sort of fits into the larger story that, not just exists within AWS storage, but within a lot of our services, which is meeting the customer where they are and not having to prescribe a solution to them. If you so desire to have this sort of, this file system like interface where you're maybe migrating and that's what your application's already built on top of, there's never a one size fits all solution, but being able to offer these improvements across many different parallel options, especially here in the HDD offerings with FSX for Lustre is extremely exciting. But I will not say the phrase for this next launch that I'm about to speak about, but it does come into play. There's another phrase I think we use a few times. Actually, I don't know how much we've used it. Regardless, let's get into the title of this launch. It is that AWS Glue launches version 2.0. I don't know if there's any nickname for it yet. I don't know if it's Glue 2, but maybe I'll use that myself. I'll talk to some folks, see if we get that implemented. But Glue version 2.0 offers a few things that are very, very exciting. The first is that it has 10 times faster job start times, and the second is a 1 minute minimum billing duration. So stage setting a little bit here. AWS Glue, sort of named very effectively for its job being a serverless ETL function. People typically refer in data pipelines to this sort of phenomena as writing glue code that sort of takes your data from its source and its destination and all the intermediary phases in between. And AWS Glue performs this operation, allows you to author code and run these jobs in a fully serverless fashion. So you get all of the benefits of that, auto scaling, only pay for what you use, so on and so forth. Now, as a part of a Glue job, there is typically a latency period between when you initialize the job and when it actually begins processing. And so that latency has now been reduced by 10 times, which is, again, an order of magnitude increase. And the AWS story that I'm trying to tie in here is that when you invest in a managed service, you're not investing and locked into the value that you get on the day that you begin implementing with a service, right? These services are continuously improved over time such that you are going to continue to get more and more value out of them as time goes on. And cutting down the start time by 10 times is a pretty good example of that. On a similar sort of level, reducing the minimum billing duration enables you to then be more incentivized to run a larger number of these workloads without having to worry about, oh, is it worth it to run this workload if I'm going to get billed for a larger amount and I'm not really getting my value or paying for the value I'm receiving. So this is just better pairing these broader philosophies around billing and performance and continually evolving and improving managed services, but for folks that are using ETL and Glue. So AWS Glue version 2.0. Hope I did it some justice. We have a link to the blog post. We'll have that in chat, so you can take a look at what that looks like. But largely, these are some benefits that you get to access without actually having to change anything in your code as they happen sort of under the hood. So some exciting stuff there. Absolutely,
yeah. I think the billing sensitivity down to the minute duration is really big because you're right. Even if typical cloud services, the billing per hour is probably pennies. So that's the case with a lot of AWS services. Even the billing per hour is pretty granular. At least for me, I always have that slight mental hiccup, like, oh, but I'm spinning it up for just a few minutes. Do I really have to pay for the whole hour? And I just love the fact that that the service team has gone and kind of responded to that feedback and has that customer obsession to say, yeah, we know how you feel. We do this all the time. And for a minute, I don't think anybody can complain about that, right? It's you get diminishing returns as you go from an hour to a minute. That's pretty big. But if you go from a minute to a second, okay, I can see paying for a minute of a service if I use it for 15 seconds. So I think that crosses a threshold for me personally. So speaking of glue code and building processes to kind of glue together your different workflows, I want to talk about AWS Contact Center Intelligence. Okay, so the 411 on this is that if you have a contact center, then you want to take a look at contact center intelligence. And what I mean by contact center is you have a call center, you're taking customer service calls, you're doing chat transcripts, whatever, right? There's a lot that goes into that. It's a huge operation. And what contact center intelligence does is it provides you kind of before, during, and after extensions and enhancements to your contact center. And I just want to go through each one real quick. So before, what we have with contact center intelligence is the ability to self-service and add on intelligence capabilities to your existing contact center. What do we mean by that? Well, for example, let's say you just have a call center right now. You can quickly and easily add a chatbot that's backed by Amazon Kendra. You can add AI-driven interactive voice response, right? You can add all these things that really cut down on the amount of manual work or the amount of manual interaction it takes to route a customer, for example. During a customer service call, contact center intelligence can also help you because what we can do there is with we can provide AI-powered speech analytics in real time. All right. What this allows you to do is to help agents kind of better route and respond to customers. So one crazy example of this might be that you have a customer that has a really, really urgent issue, right? With enough data, you can kind of figure out that how do I group these? What are the symptoms that I'm looking for, and how do I prioritize them in the queue? And then finally, we have parts of the service that can really enhance the post-call analysis phase. When you run a large enough call center, what you end up having is reams and reams of data, right? Voice data, chat transcripts, all sorts of stuff. And what we can do, again, these are all AI-powered features, is that we can find patterns and we can find quality issues, and then we can link those back to operational performance stats, all in the service of making your call center more lean and better fit to serve your customers.
Yeah. Sorry, I'm a little distracted on my end. I'm trying to work out some of the LinkedIn issues over here. Again, we dual stream to both Twitch and LinkedIn Live, so working through a little bit of that at the moment. But we can revisit that during the break. We're getting to the tail end of the opening session, so I figured I would sort of close things off with. Wait, is this the last one, or do you have another one after this?
I think you have the last one.
Ah, okay, cool. First and last, wonderful. So, without further ado, we have Amazon ECS now supporting EC2 Inf1 instances. So there's a lot of sort of layers to this this proverbial cake to understand, I guess. So let's start with the EC2 Inf1 instances. These are EC2 instance types that are powered by Inferentia chips. Inferentia chips announced, I believe, at reInvent 2018. That are purpose built to be able to optimize the processing of inference, which is one of the two phases in machine learning workloads, the other being training. So you sort of have this discrete training step where you commonly use GPUs, and then you deploy your model, and there's a lot of unique properties of that workload, namely that your model is loaded into memory. You ideally would want to share that across many different processes that can then perform inference against that, accept input, and so on. And Inferentia is truly built from the ground up to be able to optimize that inference step. And most companies, actually, when they are working with AI and ML, over the long term, inference becomes a significantly larger portion of their costs than training itself. In experimentation, when you're training, sometimes that's larger upfront. But we've listened to customers, and they want to be able to reduce these costs. Naturally, no one ever wants to pay more money than they have to, and so that's why the Inferentia chips were so impactful. They were available in the EC2 instance type that were made generally available, I believe, in the last year, and now Amazon ECS supports those Inf1 instances as the underlying capacity provider, or maybe that's not the right word, the underlying instance on which your containers through ECS are hosted. So what does this look like to use now? Well, if you're already running inference on ECS, it's actually quite similar. But in particular here with the Inf1 instance, you will have taken a model that you have already trained. You will use the AWS Neuron SDK. It's available directly in the AWS Deep Learning AMI, so you can mess around with that, or you may have already been using the Neuron SDK already to begin with. And then you can create a cluster and deploy, let's say, like with TensorFlow serving as the framework on ECS, your model that is then going to be powered and access those performance benefits of the underlying Inferentia chips. So this is much more effective to follow along with the blog post. So we'll throw the link there in chat. We have a post from Julian Simone, who does quite a lot of work with that. So very exciting, and largely sort of the broad strokes of what this means is that if you're performing inference and you're using a containerized deployment mechanism for doing that, namely in ECS already, you can simply switch you can implement with the Neuron SDK and access better price to performance for these inference workloads. So some exciting stuff. I know dollars and cents may not seem like a lot at sort of first glance, but when you're running, let's say, inference workloads on content moderation or anything that scales out to a very large number of requests, it always ends up being many zeros in terms of cost. So any savings end up being quite impactful. So, all right, well, we have rifled through our 5 launches. And we are getting to what I would say is the main course of the What's Next show, that being the 2 deep dive sessions with service teams. Again, looking forward to Amazon Bracket and RoboMaker WorldForge. We are going to take a quick break. We'll be right back. We're going to try and diagnose some of those LinkedIn issues before we come back. But hang tight, and we will be joined by the Amazon Bracket team to talk a little bit about quantum computing. Hang tight, everyone, and we will see you in just a bit. Hey everyone, welcome back. I think we may still be having some issues on the LinkedIn live side, but if you are catching this on LinkedIn, you can go over to twitch.tv/AWS to catch the action there. It seems the stream has been going strong on that side. Technical complications aside, we are very excited to have this session here. Joining us to talk a little bit about Amazon Bracket is Martin Schuetz, research scientist from the Amazon Quantum Solutions Lab. Martin, thank you so much for taking the time to talk to us about Bracket today. This is something that's very exciting for us, and I know a lot of the folks at home.
My pleasure. Thanks for having me.
Yeah, so Quantum computing. Wow, this is I said at the top of the show that we've covered all walks of life, or many walks of life here in the technology space, but quantum computing, this is certainly a first. So I am by no means the foremost expert, nor am I a research scientist at the Quantum Solutions Lab, so I figured I'd throw it over to you. In a nutshell, could you describe what quantum computing is?
Right. So the basic idea behind quantum computing is to leverage the intricate physical laws of the microscopic world, and that is, in a nutshell, quantum mechanics, to do computations in a new and improved form. So these quantum mechanical laws, they may seem very bizarre to us because we don't experience them in our everyday life, but they have been tested and verified again and again over the last years and even decades, and have helped us building up confidence in this theory, such that now we're actually ready to build a machine that unlocks these very laws. And we are very excited because, as it turns out, this machine holds the promise to provide speed ups to very hard and relevant problems, even some problems that could not be solved otherwise. So it really opens up the door to a new paradigm in computing. But before closing here my intro statement, there's one important catch that is important to make here. There's a lot of hype around quantum computing, but really I want to be clear that this technology is in its infancy. It's really early days for quantum computing, simply because there are major scientific and engineering challenges ahead of us. Still, we think it's the right time for our customers to get access to quantum computing and start exploring and experiment the beautiful world of quantum computing.
Yeah, awesome intro. I'm personally very curious. I mean, I've heard a lot of buzz around quantum computing, seen some interesting academic work that then later had to be retracted. But so it's great to have an expert like you on the show with us. Could you briefly explain the fundamentals of quantum computing? You alluded to quantum mechanics, but can you take us a little bit deeper on that?
Sure. Let me try to use the following picture. So you see, at the very fundamental level, all our so-called classical compute, from your cell phone over your laptop to even the most powerful supercomputers today, they process information in a binary form, typically identified as zeros and ones. But that's just a convention. You could also call them mom and dad, but you could also call them North Pole and South Pole. So in essence, what you have with a classical machine is so somewhat of a compass needle that can point either to the North Pole or to the South Pole. That's a classical bit. A quantum computer operates with a quantum mechanical bit, in short, a qubit. And what a qubit can do, it's a compass needle that can not only point to the North Pole or the South Pole, but it really can point anywhere on the globe. And that is it's basically a hybrid between North Pole and South Pole. It's what we call a superposition.
This is bringing me back to some of the math and engineering I did when I was in school. But with the globe example here, right, you have sort of North and South poles, but then the ability to represent sort of the quantum state, I guess, or wherever that needle is pointing on the world. Not only it's a continuous plane, I'd imagine, right? So there's yes. There's a very large number, if not infinitesimal number of values, I guess, in theory, it could hold. But then you could also represent that with something like polar coordinates in this scenario, right? Where you have like the rho, the radius, and
that's right, yeah.
Theta
lives on a sphere, spherical coordinates, yeah.
Yeah, cool stuff. So that was quantum computing 101 in 5 minutes. Thank you everyone for tuning in. But in all seriousness, it does lend a bit more weight to and understanding to sort of the computer that will then operate on those underlying mechanics, and how sort of the codification of information is fundamentally different, right? We're not talking about something that's slightly more efficient than systems that have existed before. This is building entire systems and technology and computers and in bracket APIs and ways to interact with those for a fundamentally different paradigm. And I know the word paradigm gets thrown around a lot. Maybe it's apt in many of the scenarios it is used. I think there is no more apt scenario about talking about a new paradigm than quantum computing.
Yeah, absolutely. This is really interesting. I mean, but I'm wondering, if you're talking about quantum computing being such a paradigm shift at the bit level, you're talking about a qubit, which fundamentally behaves differently from a classical bit. How does that percolate up the stack? And I'm curious about all aspects, but maybe we definitely won't have time to cover all the implications of quantum computing from scratch. But maybe you can kind of jump ahead in the queue and just tell us, like, how do you program a quantum computer? Like, what does a quantum algorithm look like?
Right. Let me actually let me share the screen, because I will pull up a little slide here to visualize this. So at its core, it's actually not so different from classical computers, which operate with Boolean circuits, right? Where essentially you can build more sophisticated, more advanced functions with core simple building blocks. So for example, here you have a function that I call Q. It's A times B. A and B are classical bits here. And I have stacked together these core building blocks in some circuit level fashion to come up with this more sophisticated function that I want to generate here. Quantum circuits are not that different. You see, the input are not bits, classical bits, but these qubits, typically drawn with, identified with lines here. So here we initialize 3 qubits, all pointing to the North Pole. And now we use quantum gates. These are our core building blocks. It's really like playing a little bit like Lego. Now you stack together these core building blocks, what we call, for example, here a Hadamard gate applied to the first qubit, a Hadamard gate applied to the second qubit. These are single qubit gates because they operate at 1 qubit at a time. We also have, in our arsenal of Lego, 2 qubit gates. Like this is what we call typically a CNOT gate. And what you figure out is by stacking these building blocks together here, starting from a very simple quantum state 0, 0, 0, you come up with a maximally entangled state where all the qubits are actually either pointing to the North Pole, 0, 0, 0, or pointing to the South Pole. So you have a new quantum state stacked together with, that's how we build quantum circuits using core building blocks.
That is fascinating. May I ask, when you say that there's this gate that operates on a single qubit, at the hardware level, what is that? I mean, because when you show the classical circuit on the left, that looks familiar to me, right? I can see that, okay, well, that's an AND gate, that's an OR gate, this is a transistor, this is whatever. Like, we know how to build that. But if I were to put the H, I forget what you call that, the H.
It's the Hadamard gate.
Hadamard gate?
It's the Hadamard gate. Essentially what it does, it takes your compass needle pointing to the North Pole and tips it into the on this hemisphere here. So in a superposition between equal superposition of North and South Pole.
Okay.
But coming back to your question, what this means, obviously now this abstracts away the physical implementation of this machine, right? The circuit level. So there are different technologies available. I will show some of them in my demo later on, and it depends on what implementation you use. At this point, we make available to our customers superconducting chips. In that case, this gate here corresponds to a microwave pulse applied to a superconducting qubit. We also make available trapped ions. These are really single ions, so charged atoms trapped in vacuum. And you shine, essentially what you do is to implement the Hadamard gate is, for example, you shine in laser light pointing at the single qubit.
This is fascinating.
This is so cool. And it's so different from what, I mean, because the transistor, we know those pretty well, right? I mean, but this is so different, even at the fundamental building block level. This is fascinating.
Yeah, I mean, like, even looking at like on the Boolean circuit, you have a given value, it accepts one or two. Like, even just the idea of a qubit and like, from what I understand about like stats and chemistry that I've learned, you sort of have like this probability density function over sort of like how likely a qubit is to be in a certain state at certain times, or like the likelihood of each state that it could possibly be in. And then the Hadamard gate almost acts like like in AI and machine learning, a lot of the breakthroughs with things like neural nets were involved the construction of these layers that would take your input and then apply basically like a sinusoidal curve to it to either push it into like either the 1 or a 0. And that sounds kind of similar to what the Hadamard gate does here with sort of the quantum state. It's and again, I don't know.
I will actually, in my demo, there are very interesting emerging similarities between deep neural networks and some of the more modern advanced quantum algorithms circuits. I'm going to cover this in our demo.
Okay, just one last question. I know this is because this is just so fascinating. One more question, and I promise we can get back on track. What would happen if I took a qubit and I passed it through 2 Hadamard gate in series?
You are back. You're back to where you started from. So you essentially, let me think. You have a Hadamard gate that brings you from 0 to 1, and into this hemisphere here, and another one brings you to the South Pole, basically. So in a classical state again.
So 2 Hadamard gates in series inverts the qubit. Is that?
Yes. That.
Or is invert even applicable in this?
Yeah, sure. You can. I mean, you can stack together whatever you want.
Okay. This is a whole new world for me. So let's keep going.
Cool. So tying this all sort of, back together, we started at the top, intro to quantum computing. I know we've weaved in now here the comparison to classical systems and, classical circuits, the computers that power them, the logic and sort of the programming that we would use to build on those systems. I know, Martin, you mentioned sort of before the show that you would show us a little about what that looks like. But before we get to that, we haven't really spoken a lot about Bracket in particular. So with all of this quantum computing sort of foundation in front of us now, how does Bracket sort of fit into this landscape? And what did we launch? Because Bracket has gone generally available this week.
Right. So Amazon Bracket is a fully managed service for quantum computing. So really what we want to provide to our customers is one-stop shop development environment that gives you all the quantum computing tools and technologies into the hands of our customers. It is fully integrated into the AWS cloud and gives you full functionality to design quantum circuits, quantum algorithms to test them against high-performance classical simulators, and then eventually run them on your choice of actual quantum computers, where we offer different technologies. So really what we want to create with Bracket is offer sort of a level playing field for quantum computing and take away all the undifferentiated heavy lifting behind quantum computing.
He said it, not me. It doesn't count.
That's right.
No, but it's great to hear. I know Rob rips on me when I said it, but I'm clearly not the only one who's barking up that tree, right? No one likes doing work that is.
Your fingerprints are all over this. I blame you, Nick.
Yeah. What's the word in courts, right? You tainted the witness or something, right? No, but I promise I did not entice Martin to say that. But again, there are enough complexities with running classical systems. I can't imagine wanting to inherit the large number of challenges to running a quantum computer. So being able to have managed service lets me experiment on that and not have to worry about that. Sounds quite enticing to me. So, you said, Martin, that you would show off a demo. I hope I'm not signing you up for something that you aren't ready for, but is there any way we'd be able to see Bracket today and give folks a chance of what it looks like to use?
Yeah, absolutely. Let me jump
Martin,
into it. Yeah.
Just one minute, one more detour right before we go into the demo. I mean, is this, so you've been involved in this space for a long time now, you're a research scientist.
Yeah.
Is this stuff still mind-blowing to you? Because when you describe it to me, just now, and other times that I've heard introductions to quantum computing, to me, this just feels like a magical new world that I've stepped into. How does it feel to you after being in the field for so long? I know that's kind of an open-ended question.
Yeah, kind of open-ended, but in a nutshell, yeah, in full honesty, I feel you get very used to it. And what is special, obviously, now is I think it's a very special time for quantum computing now that these machines become available, even if it's really very early days. But maybe that's also what makes it very, very exciting.
Awesome, thank you. All right, on with the demo.
Okay, great. So what I'm showing you here is the Amazon Braket landing page in the AWS console. Comes with some information how to get started, shows you a little bit how it works, so the core building blocks, the modules that we offer on a high level to build quantum circuits, to test them on classical compute, to run them on quantum computers, and then post-process and analyze your result. Comes with information on pricing and additional links on the documentation and FAQs. I recommend to take a look to get started. Then obviously an interesting tab here are devices, and these are now the quantum computing devices that we offer to our customers as of today. We have one cloud-based managed simulator that's classical compute that emulates a quantum computer. And then we offer 3 actual QPUs at this point in time. There's a quantum annealer by D-Wave. I'm going to run an example for this one. There is a trapped ion-based machine, IonQ, and a superconducting machine from Rigetti. And if you click on these, you find more information on the number of qubits. And for example, what you see here is the actual topology of the chip. So this really shows you how the qubits lie on the actual chip, and the gray bars shows you the connections between these qubits. So then a natural point to get started for our customers would be to click on notebooks over here and just create a notebook instance. You can give it a name. You can choose a notebook instance type depending on your needs for your workloads, and then it will spin up a hosted Jupyter notebook with our own SDK pre-installed. So you can really, with one click, you can get readily started and build your circuits and run them against different backends. But what I want to show today is that you can also interact with the Braket APIs from any of your preferred local IDEs. So what I've prepared here is, so this is my Jupyter file system on my local laptop here. So we can hit these and work with these APIs just from our local machine. So let's get started with the first notebook here. Just a couple of boilerplate imports that I don't want to talk about here in detail. Then we set up an S3 bucket where all the results of our quantum computing simulations and runs will be stored. So if you get onboarded to Amazon Braket, by default, it will create a bucket that is called Amazon Braket and have your account ID in it. That's the one that I'm using it. And now let's just get our hands dirty and build the very first quantum circuit. So the gate set that we support with our SDK at the moment is listed here. So these are basically the core Lego building blocks that we have, that we offer to our customers. You can stack them together. So one example here, a very paradigmatic example, is a so-called Bell state. It's just very simple, 2 qubits. And now we apply this Hadamard gate to the first qubit and then a CNOT gate between the first and the second qubit. So what happens is we first tip the first qubit into the plane. So it's in a superposition between 0 and 1. We haven't done anything to the second qubit. So now we are in this quantum state. Then we apply a CNOT gate that flips the second qubit if the first qubit is a 1. So nothing happens to this state, but we flip here the second qubit to 1 because the first qubit was in 1. And really, to do this in practice is very simple. With this simple syntax, it's just one line. So we instantiate here a circuit object. We call it Bell. and then we attach a Hadamard gate. We apply a Hadamard gate to qubit 0, followed by a CNOT gate between qubit 0 and 1. We can print this circuit to make sure it really coincides with what we had in mind. And then we can now run this circuit against different devices. So let me first use the local simulator that comes with our SDK, meaning this runs locally on our laptop. The advantage being obviously low latency, so it really allows you to do quick and dirty small experiments. It is free of charge, and you can work anytime, you can work offline. Then to run the circuit, it is really just this one line. So device.run, and we insert here, we pass the spell circuit, and we ask for 1000 measurement shots, and then we want to retrieve the results. So let's run this here live. It's already done because it's a small circuit. And again, we see, as expected, the smoking gun of a Bell state, about a 50-50 split between 0, 0 and 1, 1 and 1, 1. So perfect correlations between the two qubits, the kind of smoking gun here for the Bell state of maximally entangled state between these two qubits. We can then move on and use a cloud-based simulator, where the advantage is now that we really are not bound anymore to our local machine, but we can really fully leverage the AWS infrastructure, in particular, use elastic compute to run many multiple circuits in parallel, and store automatically all results reliably in S3. So the only thing I have to do now is to redefine my device object, and I now set it to use our cloud-based simulator. So now again, it's device.run. I run the very same circuit now in the cloud. So this takes a little bit longer because obviously there's a little bit of latency until this is finished and comes back. But obviously, when you run very large circuits, this will not be the bottleneck of your overall timing budget. Again, the expected results. Now, every of these execution, this is what we call a quantum task. It comes with basically a unique identifier, an unique ID, ARN. So I can grab this and go into our console, filter by task, look for this ID, even days, weeks later, whenever, and find all the information related about this task here in the console. Again, I can also pull all the results stored that are associated with this task in S3. So everything is stored reliably here and not lost. Now let's get to the interesting part here and actually run this on quantum hardware. It is very simple. We just redefine again our device object. Now let's use INQ and call then basically device.run on INQ with the very same circuit. So nothing else required from your end. And we can check the status of this job, which has been created and is now in the queue. These are they're very scarce resources, single-threaded machines, so it's in the queue. While we wait for this to be completed, we can always take these unique identifiers, this ARN, to later recover a task. That's what I do with another INQ task that I've run before. Let's just recover that and then analyze the results. So by now it has been completed. 1,000 shots were taken on INQ. We see it's not perfect. It's not exactly the same what we had with the classical noise-free simulator. And that is showing you the state of the art in quantum computing. We have to deal with noise and this and decoherence. So there are imperfect results. That explains why we also have some counts here in 1, 0 and 0, 1 that we would not expect under ideal circumstances.
Before we go into the next example, could we at least just like explain a little bit about those challenges? So, because I described before, like I can't even imagine the difficulty of running a quantum system, given what I know about the challenges of running classical systems. You mentioned decoherence and some of this. I don't know if it's uncertainty, what have you. Could you just very briefly talk about some of the challenges that, let's say, like IonQ and some of these other hardware providers are actually working to tackle on behalf of anyone that would have to do this themselves?
That's right. As I said at the beginning, there are major scientific and engineering challenges out there. I just briefly mentioned decoherence. So what that means is, and that's a very important one, what that means is that we talked about that quantum qubits encode information like, compass needles that are allowed to point anywhere on the globe. But now let's say there is some undesired magnetic field, maybe the Earth magnetic field, that will influence this compass needle. So it starts to shake, and obviously you will, decohere and lose information because of this undesired effect, because the needle is not pointing to the location anymore where you wanted to have it. That is one of the biggest problems. So really, that explains to you why, for example, this ion trap machine sits in ultra high vacuum, shielded from all undesired effects. You have to take care of Earth magnetic field potentially, etc. These kind of things, simply because these systems, these are really single atoms, single ions, and they are very, this encoding of information is very fragile.
Awesome. Yeah, thanks for that. I know there's a lot of people that have worked with sort of on-premises sort of systems themselves that have faced a lot of traditional computing server management problems or infrastructure management problems, and what you're describing with decoherence is just like another level of challenges that most people, again, like you said, the research is evolving, right? There are no perfect answers to this, but leave that to the experts that are managing those back-end hardware providers.
Right. So then let's just move on with a little bit more advanced example. It is basically the many qubit version of the Bell state, the so-called GHC state, which plays a very prominent role in many quantum computing protocols, in quantum sensing. The circuit itself is also very structured. It has basically the same structure as the Bell circuit. It's just an extension thereof. Again, you apply the Hadamard gate to the first qubit, and then a series of 2 qubit CNOT gates between these nearest neighbor qubits. So to this end, we define a simple helper function that, using bracket, creates a circuit object, applies a Hadamard to this qubit 0, and then a series of CNOT gates in this for loop. So let's just, for concreteness, take an example with 10 qubits. Again, we can print the circuit. This is what it looks like, and run this on the local simulator. Again, very simply calling device.run and passing on our circuit. And in fact, what we see is the smoking gun of a GHC state. You see we have 10 qubits here. In principle, there are 2 to the 10 potential bit strings that could come out of this. But for this highly entangled state, the only ones that we get is that either all qubits are in 0 or all qubits are in 1. And we have about a 50-50 splitting between
the world. So
one advantage of the managed cloud simulator I wanted to highlight here is that we can obviously now run very larger circuits. I'm going to run now, GHC states between 25 and 30 qubits, and I can, using elastic compute, I can run them in parallel. So now basically I submit a task for 25 qubits, 26 qubits, 27 qubits, etc. They are created, and now they are starting to come back. You see all of them showing the smoking gun signature of the GHC states. So this obviously helps you improve to quickly iterate and make experiments if you can run many of these tasks in parallel, as we have done here. This concludes the first part of my demo. Now I wanted to come back to something that we discussed briefly at the beginning, the analogy between these new family of hybrid quantum algorithms and deep learning. So these hybrid quantum algorithms essentially are embedded in a larger classical computation. So they work as a co-processor in tandem with a classical computer, a CPU. The idea being that you only leverage them for very short bursts of the calculation, and thereby trying to efficiently limit the effects of undesired noise and having parts of the computation done on the classical computer. So this is really reminiscent of what happens in deep neural networks, where typically you say you have some objective function you would like to find the minimum of, say the error on your training set. So we typically start out with some random guess for your parameters. This defines your neural network. You then execute this, this computation on the specialized hardware, the QPU, which does what it's best at, namely matrix multiplication, and then passes back this objective function to the CPU, which then takes the next educated guess for these parameters in a for loop until your algorithm converges. And exactly what happens here in these new hybrid variational algorithms. So what I showed you so far, essentially we had these single qubit and 2-qubit gates, and they were essentially hard-coded instructions. But the idea being here is that they take in some parameters, but leave it to a classical CPU to find the optimal values for these parameters.
This is super interesting because you know, I do a bit of work with AI and ML, and this not only the visualization you show machine learning on there, but something that felt similarly sort of new to developers as a paradigm and these sort of models was when TensorFlow first sort of came onto the scene, and folks had to learn how to sort of operate with this computational graph model. You had to sort of understand the DAG, the direct acyclic graph. You sort of construct the whole graph, and then the training phase is essentially just executed with like a graph.run or graph.fit, let's say, method. And it's quite interesting because these experiments or these tasks in the quantum world seem quite similar, even if those graphs look a little different. They use quantum circuits. They don't use bits. They use qubits. It's and maybe that's why you alluded before that these can become quite similar in some of the ways that they approach these problems.
Yeah, and actually our hope is that we attract a lot of interest from data scientists, machine learning experts, deep learning experts, who potentially don't have a formal background in quantum computing, but they will we think can very quickly pick up on these kind of concepts because there are these very strong similarities. And with Amazon Bracket, we think we can make this sort of learning very easy.
Martin, we have a question in Twitch chat. Is this quantum sim or connected to a real thing?
So you can do both. As I tried to explain previously, it's really just changing one line of code, redefining the device object, and then you can either run your code on a quantum simulator or actual quantum hardware.
Awesome. So why not both, right?
That's right.
And I would say that makes sense, right? Like, let's we haven't talked about pricing, but I'd imagine that if you could sanity check, let's say the task that you want to run and make sure that at least in the simulator locally it's working before you go and deploy that and potentially have an expensive mistake.
Exactly.
That's in AI and ML it works that way. Maybe you run your training and just make sure that it's not getting an out of memory error, but you're not gonna let it sit there for 50 epochs, and as soon as you know, all right, yeah, this will work as I understand, then you go and deploy it and scale it up to the quantum backend.
That's exactly the spirit. Yeah.
Cool.
Yeah, and I just also wanted to part clarify, part fact check, but the hardware that we're talking about here, they're not kind of all apples to apples, right? They have different capabilities and different workloads that you would run on each one of them, right?
Yeah, so what we offer with the 3 quantum backends today is a quantum annealer by D-Wave. The demo is yet to come. And this is a different paradigm from the one that I'm showing you today, which is circuit-based. You know, circuit, this is a quantum circuit, how we typically draw these. And IonQ and Rigetti are circuit-based machines. So as an input, you give them a quantum circuit, and that's what they would like, that's what they can execute on. I mean, physically, they are very different, and they have very complementary you know, advantages and disadvantages. So for example, I mean, Rigetti superconducting chips are very fast, but typically you only have only nearest neighbor interactions. Ions are typically have a slower clock rate, but these are really very pristine, high quality qubits, which offer all-to-all connectivity. And so what you can do as a user here is, you know, you just you build your circuit, you build your quantum algorithm, and then it's just about changing one line of code to compare the results from these different approaches to quantum computing and see what fits best for your particular use case.
Love it. You're making me sound right when before I said we meet customers where they are. We don't prescribe. We want to be able to offer them the options that they see out in the world. So just making me look good, Martin. You said the forbidden phrase before about undifferentiated heavy lifting.
Yeah.
It's wonderful. You're a great guest. You're doing all great work. So that was, you know, you showed us the circuit-based solutions there. You did mention quantum annealing. I think if I remember correctly, through D-Wave. How is that different? Is there any way you could show us what that looks like comparatively to circuits?
Let me very briefly finish this here.
Okay.
Just a very quick walkthrough. So what we do here is we make a specific ansatz a circuit which takes in some parameters, and with a classical CPU, you try to optimize these angles or these weights. The specific goal that we set out here is a graph coloring problem. Now, this may look like an academic exercise, but actually it turns out that you can map relevant problems like, for example, portfolio optimization in finance or clustering in marketing on this type of problem. So what it means is I have this graph here with blue nodes and some edges connecting them. And the goal is to color every node either blue or red, meaning, for example, is this customer here in segment A or segment B, in cluster A or cluster B? And you score a point whenever you have an edge connecting a blue to a red dot. So that's an optimization problem, a combinatorial optimization problem. And we run this here using the specific ansatz QAOA. It is a circuit. You can relatively quickly define the circuit, and it takes some parameters. And given these parameters, we then build the circuit. And these parameters are, you know, first we can again print the circuit for a given set of parameters, has 2 qubit gates and single qubit gates, and then we run a training method here that will take as an input a specific device you would like to use, and then it goes back and forth between the classical optimizer and the simulator or the QPU backend until the algorithm converges and gives you some solution of red and blue nodes. So let's quickly visualize these. That's the solution that the quantum algorithm has come up with. Some of our customers are, you know, in the blue segment, others are in red. That's the final solution that the simple toy model example has come up with. Obviously, you don't need a quantum computer to solve this, but we can benchmark here against classical simulations and convince ourselves that the quality of the result is the same. Now, what's interesting with Bracket is that this broad problem family of graph coloring problems I can also run with D-Wave. So again, that's the last part of my demo. Again, some boilerplate of packages I need. I set up my S3 bucket, and now I set my device backend to the quantum annealer by D-Wave. Here, this machine does not expect a quantum circuit. It essentially expects a matrix that encodes our problem. So here we take, again, in this case, a graph with 5 nodes and some edges connecting them. The full problem formulation is this simple dictionary that encodes essentially the weight of these edges. And then the main code are these 3 lines. So we set up the device, which is a sampler. That's because D-Wave essentially samples from the low energy subspace or the kind of most likely good solutions. We then put this into an embedder. Embedding meaning we put this problem on the D-Wave graph. The D-Wave machine has a very particular physical structure. It's called a chimera graph, shown here. It consists of unit cells with 8 qubits each and these highlighted connections between them. So the embedder helps us put this problem on this particular graph, and then we just call for a response with sampler, sample this QUBO problem, QUBO meaning quadratic unconstrained binary optimization problem for this given Q matrix. So let's just run this. This now goes into the cloud, runs on D-Wave for this particular problem. Now it's done, and this is the result for this graph coloring problem. So it suggests to color some of them blue, some of them red, and again, here you see you score a point whenever we connect red to a blue node. So we score here, we score here, we only have to take a hit here, and actually we have to take a hit here because if we color this red one, we would take a hit here. So that's the optimal solution with an energy of -5 and the optimal cut size for this simple problem. The upshot being, again, we can now use different technologies to solve problems. In that case, a quantum annealer for the sort of problem that we attacked earlier with these hybrid circuit-based quantum algorithms.
This is super interesting. Graph theory was my favorite class in school, and remembering a lot of the methods I learned, which I guess were inherently classical for solving these problems.
Yes.
It is so interesting to see this done in a quantum manner, and I can't even imagine sort of the way that those algorithms look, because the classical computing algorithms for some of these graph solving problems are complex and hairy enough. So this is, I'm geeking out. Sorry, this is really cool. Your point before about graph coloring problems or graph problems broadly being applicable is, you can't undersell that. Like, data exists in graphs much more than most people think. So you have the traveling salesman problem, you have the Knight's Tour, you have lots of different fun problems that real world problems can be modeled as, and I think we'll have you talk a little bit about some of those, or at least a little bit about what the Quantum Solutions Lab does on the tail end after you end up talking about. Actually, no, this was the quantum annealing example, right?
That's quantum annealing example. So
cool.
The demo, we are done with the demo for today.
Awesome. Yeah. So just connecting this these kinds of graph problems, maybe you could talk a little bit more generally about the complexity theory. The complexity classes that we have, and talk a little bit about the class of problems that quantum computing in theory could speed up. Is that something that you want to take a quick minute to address?
That's a tough one for a quick minute, but so you see this problem, for example, is an NP-hard problem, where essentially the problem is, you see, as the number of variables increases, the number of potential solutions increases exponentially, right? It's 2 to the, you have 5 nodes here, so there are 2 to the 5 candidate solutions, 32. If I add just one node, then it's 2 to the 6, 64, and it goes up very quickly, exponentially. That's basically the problem. The very basic promise that quantum computing here brings to the table is the superposition principle, namely that as classical compute runs out of steam because of this overwhelming number of candidate solutions, is using superposition is that it can basically scan the entire solution space in parallel, being in a superposition of all potential candidates, and then you have to play some tricks. That's a little bit too advanced here to sort of amplify the amplitude along the best possible solution.
Yeah, and my understanding is that, or at least what I've heard is, some of the ways certainly that we do network security, for example, rely on the assumption that these problems stay hard to solve, right?
Mm-hmm.
So I think a good one would be prime factorization.
Yeah, so I mean, this is what sort of kick-started the whole field early on with Peter Shor in the 90s, showing that there is an exponential speed up in factoring very large numbers. So this seems very academic, but it's essentially the mechanism behind, you just said it, behind RSA encoding, behind security. And a quantum computer could just crack these problems very efficiently in minutes. That just would take the age of the universe on any supercomputer. But the caveat, I have to be very clear about this, is yes, this kickstarted the field, and we want to be there to unlock these exponential speedups. But this will require effectively to fully control hundreds of thousands or millions of qubits, and that will be a long road with many scientific and engineering challenges along the way.
Mm-hmm. And like you said, well, I mean, what we saw with the D-Wave machine at least was 2048 qubits, right? Are we comparing apples to apples there?
No, not really. We should be careful. Shor's algorithm is designed for a circuit-based machine, and circuit-based machines at this point in time, these are universal quantum computers. They have very hard, very tough engineering requirements. That's why they are in the regime of 20 to 50 qubits or something like that. The engineering requirements for quantum annealer are more relaxed. That's why physically they have 2,000 qubits, but it's not in a sense a universal machine that you cannot readily run, like, for example, Shor's algorithm on this annealer. It's more specific purpose, tailored towards the sort of optimization problems that we just discussed.
Okay, so are the IonQ and the Rigetti hardware examples of this general purpose quantum computer?
Yeah, exactly. Yeah.
And so can we compare the bits, the number of qubits that they can support in line with this problem of Shor's algorithm that you're talking about?
Yes, absolutely. So let's click on devices in the console, and it shows that IonQ as of today has 11 qubits, and Rigetti comes with 30 qubits. I want to emphasize here that we should not only talk about the number of qubits. That would be oversimplifying. It's just one dimension. It's the quantity. Quality is another important dimension. And there are discussions, fights about what's the right metric, etc. At the end of the day, I think the big milestone will be to show quantum advantage. So really showing quantum advantage in an industry relevant application.
So on the academic side, can you give us a peek at what the major hurdle is? I mean, you mentioned, if we could theoretically scale up one of these general purpose quantum computers to hundreds of thousands of qubits, then we might be able to, maybe I hope I'm not misusing the term, but we might be able to prove some of the predictions in Shor's algorithm, right? Is that what? But what
on
is
the theoretical side? I mean, I think once we have such a machine, it will probably unlock a gigantic scientific curiosity and new inventions. But obviously, we don't want just to run Shor's algorithm, right? If we have, theoretically speaking, such a machine. So we also have to make the, contributions, developments on the algorithmic side. There are some other ones, for example, Grover algorithms that can give a quadratic speed up to search problems. But really, it's just a few ones so far, and we will have to come up with other algorithms, new algorithms. I think the whole community will help. That's why we sort of, are very happy and excited to sort of democratize quantum computing and give it into the hands of everyone, of all of our customers, to help contribute to this scientific challenge.
Yeah, and that's a great segue. I know early on in the broadcast, we introduced you as a research scientist at the Amazon Quantum Solutions Lab, if I remember that correctly. Mm-hmm. So now that we have all of this behind us, we're talking a little bit about trying to then, eventually build business relevant applications. Can you tell us a little bit about what the Quantum Solutions Lab is, and I guess namely, what you do day to day? Because you've acted as instructor and educator for quantum computing and showed us Bracket, but what do the folks over at the Quantum Solutions Lab do?
Well, I guess part of my job is to act as an instructor, so really the main mandate of the Amazon Quantum Solutions Lab is to engage and work collaboratively in deep long-term research engagements with our customers. So the way we approach this is, we take a specific use case, for example, some optimization problem, and work backwards from there, building small quantum prototypes along the way, obviously build up the in-house expertise, knowledge around quantum computing with our customers, and to provide what is also one of our mandates of the Quantum Solutions Lab is also to provide a transparent view of where the field is today. And that is why we always try to benchmark the quantum computing results, these proof of concept studies, with state-of-the-art classical solutions. This could be machine learning, this could be HPC. So we always try to fan out also in these adjacent areas to provide a transparent view where the field is to our customers, and then together develop a match plan, a broader strategy around quantum, how to position themselves, and how to get quantum ready for the future.
Wonderful. So for folks that are looking to get started with Bracket, I know it is now generally available. I think we have a link in the chat to the upcoming webinar that the team will be hosting. So if people are looking to learn a little more, get maybe hands-on with it, or see some other examples, I'm sure they'll be able to see those in that webinar. It's on August 24th at 10:30 a.m. Pacific. You can register through the link that we provided in the chat. Otherwise, Martin, anything else that we missed on Bracket, quantum computing at large? I know there's only so much time in the broadcast, and you've done a great job of sort of getting everyone up to speed, us included. Rob and I definitely not quantum computing experts, but we've read some things here and there, so hopefully that helps to sort of stimulate the conversation a little bit. Are there any other resources we should point folks to about Bracket?
Really, I think that the best way to get started is just, spin up a hosted Jupyter notebook here, and get yourself your hands dirty. This will spin up a hosted notebook for you, and then you can just readily run the kind of examples that I run with you today.
Wonderful. Well,
awesome. Yeah. Thank you, Martin. This is fantastic. I'm really excited about this. And thank you so much for the crash course in quantum computing.
Yeah, thanks for having me.
Awesome. Well, with that, concluding our first demo of episode 10 here at AWS What's Next. Again, joining us was Martin Schwitz, research scientist at the Quantum Solutions Lab, teaching us a little bit about quantum computing, Bracket, and getting hands-on for us. We will be taking a very quick break, so hang tight. When we get back, we'll be talking a little bit about Amazon RoboMaker WorldForge. This is something that launched just this week. I won't spill the beans on what it does because we have a very special guest that will walk us through exactly that. So stick around, we'll be right back. Hey everyone, how's it going? We are back with our second and final demo of the day here on AWS What's Next, episode 10. So joining us for this very special session is Anabell St Vincent, Principal Solutions Architect over on the AWS Robotics and Autonomous Services team. And she's here to talk to us a little bit about Amazon RoboMaker WorldForge. This is something that launched this week. I'm very excited about it. I got to read a little bit in the launch blog post, but I figured we could toss it over to you. But before we get started, Anabell, thank you for joining us. I know you're probably quite busy, especially with a recent launch, so we always appreciate service team folks coming out and helping us with this.
Yeah, it's been a busy week, but thanks for having me on. Hi, everyone.
Welcome to the show, Anabell.
Thank you. So yeah, it's been a really interesting week. We just launched AWS RoboMaker WorldForge, which is a new capability that makes robotics testing in simulation and training and synthetic data generation much easier. So WorldForge makes it faster, simpler, and much less expensive to create multitude of 3D virtual worlds to simulate your robots in. So this, yeah.
I was gonna say, you had me at less expensive. Anytime you launch something that says, hey, you do this already and you can do it for less money, I'm sold. Yeah. I'm on board, right? But you said 3D worlds, creating those in an easier fashion.
Absolutely.
Yeah, why don't we talk a little bit about that? I mean, this is the full title is RoboMaker WorldForge, right? So folks may not be familiar with RoboMaker, but what kind of 3D worlds are we talking about here?
So we're talking for this initial launch, it's focused around inside houses. So these worlds are made up of rooms and apartments and some bigger houses, which I'll show you a bit later during the demo session.
Yeah, my world would be pretty easy to simulate. As you can see around me, I just live in the lobby of an Amazon office and just do all of my streaming from here. So probably easy to simulate, but maybe we'll get a glimpse of what that looks like later. So gonna do some more sort of base building here. So we're talking about WorldForge, which simulate 3D worlds more effectively. This is a feature of RoboMaker broadly. So can we talk a little bit about how sort of these two things fit together? I mean, I'd imagine that RoboMaker is the larger umbrella service, and then WorldForge sort of fits into that a little bit.
Absolutely.
Yeah.
So AWS RoboMaker was actually launched at reInvent in 2018. So that was it was a brand new service then. So what it provides is a complete cloud solution for robot developers to simulate, test, and securely deploy their robot applications at scale. It enables the customers to test their robot apps more easily in simulation. And they can do better testing, they can do more testing, and in order to hit any of the edge cases that you might have when you're going through your regression testing as you're iterating through your development life cycle. So what WorldForge has done is brought this capability to create these 3D worlds so you can simulate your robot in hundreds of worlds concurrently in simulation, so then you can have better quality robot applications that you produce. And as a result of that, you can generate synthetic data that you can use to improve your code, or you could use it to do analysis, but also it's good for regression testing and also reinforcement learning. So
this is super exciting. I mean, this is essentially like the RoboMaker broadly. It's not like the virtualization of these simulations. And you know, you mentioned cost, you mentioned speed, the ability to test in parallel, let's say, regression testing, all of this. You know, when we talk about robotics, I think everyone probably has a different sort of idea that comes to their mind. And maybe I'll throw the one that comes to mind for me. You know, if I'm thinking about robots and a use case where they're used, I'm thinking almost like autonomous house cleaning, right? Like a Roomba.
Good example.
Yeah, I think they're an AWS customer. Am I mistaken, or?
They are. No, they are a customer. And as part of this, so we announced the WorldForge as part of our first ever Cloud Robotics Summit, and we had Mark Cedron. He's the manager of simulation team at iRobot. He also presented on Wednesday. And he mentioned that how they've been using RoboMaker and has improved their testing cycles that they've been doing, and also how they're looking forward to using WorldForge to be able to have a more diverse groups of worlds to be able to test their applications in as well. Just to give you an indicator, they test, they simulate, run simulations, 60 simulations per build, and they have lots of builds and they have lots of different robots. So they actually run 5,000 simulations a day. So he said that in his presentation. It's on YouTube. You can go and see it later. But yeah, so this has improved their the quality of the robots that they're building, of how they operate, and also like the speed of deployments of their applications.
Yeah, let me just kind of play that back to you, make sure I understand what the customer benefit here is, right? So you're saying that they're running 5,000 simulations a day, and these are all in virtual environments.
Correct.
And what this is helping them do is to catch defects before, let's say, a new behavior, a new navigation system is deployed as a software update to their robot fleet, right?
Absolutely.
Because a lot of us have Roombas, a lot of us are iRobot customers, and they're constantly improving the capabilities and the intelligence of their robots. Now, part of what they can do is certainly take the telemetry from their fleet in real time, or I don't know how they collect their data exactly, but also part of it, I think what you're describing, correct me if I'm wrong, is that we have this full suite of simulation that we can use to kind of get them partway there and not rely entirely on real world data. Is that a fair assessment?
Totally.
I was going to say, like, the journey from on-premises to cloud is monumental for a lot of customers for a lot of different reasons, but I'm almost trying to imagine what mass scaled out simulation across many different environments looks like. And I'm just imagining the scenario in which there's like this massive building in the middle of like the the desert or something, and then they just go, all right, yeah, I've got all of my robots, I'm going to test them in every one of the rooms in this building that's engineered to be slightly different. And if that sounds absurd, it's because it is, right? Like the sort of world before simulation was largely that you just operated without all of the data. Otherwise you would never have the full suite of data to ever go out and say, yep, we've checked on everything. But that's where simulation comes in. And I think that's where WorldForge is going to shine here today, right?
Totally. I mean, that's where RoboMaker has also improved that whole experience for our customers, because traditionally you would have had to build your application, then either copy it to an a USB drive or connect to your robot to deploy the app, and then run some tests. So you have to also create the environment around that robot to test it. But with simulation, you can do that in simulation, get your data, and do it concurrently. So regression testing is definitely a huge factor here, that you can keep iterating over your code, make sure the new code you'd released didn't break it, that all of a sudden it stopped recognizing the couch and it's going to smash into it. You know, those things are definitely, RoboMaker as a whole has helped that. And now with WorldForge, you can do that in 3D worlds that are simulated for you at a large scale. Because traditionally, to be able to even get into simulation, you have to create these worlds, and these need specialized skills. Like you need people that know how to create 3D worlds. So it's a specialized skill. You need people that understand different simulation engines to be able to effectively create this. So WorldForge simplifies that you don't need those skill sets, and you can just by just 3 clicks, you can create a 3D world and then run your application in simulation.
Yeah, definitely. Now, every time I partake in a conversation about robotics, it's not long before somebody brings up the robot operating system, also known as ROS. How does that fit in here?
Yeah, so ROS, or Robot Operating System, it's an open source framework. It's probably the oldest and widely used operating system per se, but again, it's a framework that sits on top of Linux. That's what people were seeing huge adoption of it globally within the robotics companies. And recently, last month actually, so ROS2 Foxy Fitzroy distribution was launched, and that launch was specifically focused on making sure the distribution is production ready. it comes with security and reliability, which are the key factors when you want to deploy production-ready applications. And AWS has also contributed to that distribution as well. There's many distributions, but this is the most recent and most reliable and future-looking version of ROS. In addition to that, AWS has also developed cloud extensions, ROS cloud extensions. And what that does, it makes it easier to extend your robot applications to use either AWS services. For example, like Polly for speech generation, Lex for speech recognition, or Kinesis for video streams, right? And we've got CloudWatch extensions as well, where you can collect your logs from your robot application in simulation and also from physical robots, and as well as the metrics. So they're all, you can see all your logs in one dashboard collected together, and you can, again, run analysis on them. And the most recent extension that we released is an S3 uploader, which is what it actually does, it actually records ROS bags. ROS bags is a term, I guess, within ROS that you collect data and sensor data, for example, and you can push that directly to S3. So these extensions help robot application developers to extend their application and leverage AWS services to have a more comprehensive and fully functional robot applications.
Yeah, I mean, it sounds very exciting. I mean, the promise of standardizing an interface or a framework around these common, let's say, input and output aspects of robots, like, there's a microphone, and then the ROS framework enables sort of the ingestion of that audio stream. And then, hey, look, we can use something like transcribe as the cloud module on AWS to then, or the ROS cloud module that enables us to send that signal out to transcribe. And you can just more quickly power your robot applications and your robots themselves with these other services that AWS is building for, let's say, traditional workloads. I don't know if robots would not technically be a traditional workload, but you get what I'm saying.
Absolutely.
So really cool. You mentioned before sort of this paradigm of building, testing, deploying, and simulation, which is really the star of the show today. But to give people a flavor beyond my ridiculous scenario of buying out a hotel in the middle of nowhere to simulate all my robots on, what does build, test, deploy really mean in robotic development?
Yeah, like I mentioned before, like previously you had to you build your application so that you generally would build it on your own laptop. So you build the app, then you have to package it in a format that your robot will understand, copy that to the robot, then run your app, and again, create the environment around that and validate what you just tested. And if you've got a small bug, then you have to redo all of that again, right? So I guess that's more the traditional way of developing robot applications. But as with simulation, that's where the power of simulation helps that process. And being able to do, I guess, simulation on its own, you can do that, absolutely. You can simulate, Gazebo is one of the simulators that is open source, and you can run that on your own machine. But, some worlds or some applications need a lot more compute capacity. So then maybe your machine doesn't have the capacity. Or you want to run multiple simulations, concurrent simulations at the same time. Again, you can't run it, or you need the infrastructure to do that. So that's where RoboMaker comes in, where you can, it's a managed service, undifferentiated heavy lifting is done for you. I just wanted to throw that in from the previous session. So it's a managed service, so we scale with your simulation, and you can run concurrent simulations at the same time. And that's the bringing the power of cloud to robotics, and it's a game changer when it comes to the robotics industry, for sure.
I love it. I don't have to say anything today. The guests do all the work for me.
You don't. However, I will tell you that in the fullness of time, you will slip up.
Fullness of time. All right, we're just throwing in all the slogans today. I love it.
And of course, And of course, it's pay-as-you-go pricing, right? It's true though, but so simulation, you pay for the simulation that you run, and you can specify how much CPU, how much memory you want to allocate to it. And if it fails, you see it fail, you can just stop it and stop paying for it. So
yeah, on the topic of simulation, we've talked about how this enables you to or customers that work with robotics and want to be able to perform these simulations, there's a let's say orders of magnitude cost reduction and operational or time reduction. But something else that starts to come to mind for me is that, like, what if the location that this application would be deployed in does not have an easy way to test in, right? So let's say we're like, I don't know, like let's say I want to train a drone. Underwater is a good one. I was saying, like, if I'm going to train like a drone and I fly it over a volcano to test it and it just falls in, and then oops, that was an expensive mistake, right?
Absolutely.
So is this something that we see customers looking to something like RoboMaker and even WorldForge to help them with?
Absolutely. I mean, that's one of the reasons. So I guess from an expensive part, testing physical robots is expensive. So so if you're, like you said, if you crash your robot, or if it falls in a pond, or there's a lot of different factors. So it crashes into a tree, so there's a lot of reasons why this can be expensive. And like even the robot arms, like they're very expensive devices, and you don't want to be testing on those so frequently. So that's where definitely simulation helps that. But you still have to do some physical testing. It's not going to be without saying, because there is different fidelities so available within different simulation tools. So lower fidelities, medium, if you need like really precision, for example, like vibrations that you need to test against, there's some things that you need to do on physical robots. It's not going to happen. You can't do everything in simulation, but you can get majority of your bugs out before you actually deploy it to the robot.
We can simulate the phenomena, we can model and quantify, right? That's we can only test what we can simulate and what we can understand, but we know that the real world always data is dirty in the real world. That's kind of the saying in machine learning, at least. So
and I guess we've started with WorldForge being a like inside houses, indoor space, but this is the start, right? So the opportunities out there, what do robotics companies want to simulate? What worlds do they need? Is it hospitals? Do you need different types of layouts of hospitals to validate your robot that's going through maybe cleaning the hospitals, or sterilizing the hospitals? Planes, do we want to sterilize planes, and what do the formats of those look like? So this is sort of starting that opportunity to see what customers want. And as you guys know, 90% of our capabilities and services are based on what customers need. So this is the start, and what the customers ask for, that's what we're going to focus on and build for them, so we can make the robotics companies effort easier to be able to build and deploy great robots out there.
Awesome. And I could pretend like this is a question I don't already know the answers to, but when we're talking about making these environments indoors, especially with WorldForge and being able to create these to power these simulations, essentially, WorldForge was released as generally available this week, or was rolled out to regions that RoboMaker is available in this week. But it sounds like something that's very visual, and anytime there is something visually oriented like that, I know I learn better by just seeing it in action. So would you mind showing everyone?
Absolutely, happy to. All right, let's get. Okay. All right, so this is the RoboMaker. Okay. All right. This is the RoboMaker console. So I just want to show you, I'm in the Oregon region just for this first part of the demo. So this is, you can see here, WorldForge new. This is what we just launched. So this is the new part of our console. So if you go to World Templates, you can go and click on a template. Here you can see the different types. So this is a sample of a world, like a house, and there's connections that happen between the rooms, and there's different materials and furniture. So I guess that's another hard part, right? When you're doing this in simulation, you have to generate all these furniture and materials for simulation. And then there's the concept of where your robot starts. So there is a default location for these worlds that I said, where when you start your simulation, your robot will start in that location. So that's what that green button is. But let's just quickly just show you what there is. But how quickly can we build a world? So we've got some templates. So this is, first one's just a bedroom. And then we have a living dining room template as well. We have a 1-bedroom apartment. So you can see there, and a small house. So what I'm going to do is quickly, I'm going to say start. Let's try a living dining room. I'm going to say generate world. And floor plans, I'm going to choose there's different types of floor plans you can use. Again, these are randomized. So, and 2 different types of interior variations. I'm going to say generate. So there, my worlds are being generated. We're going to go through, create another one. This time, let's choose the 1-bedroom apartment. Let's say start. I'm not making any changes here. I just want to show you how quickly these things come up. I'm going to do 2 here, 2 here. Click generate. Right. And then we'll do 1 more of the house.
And while you're creating these, I guess to reiterate for everyone who may be watching, the idea of being able to have WorldForge automatically do the varied environments through just simple variables here, right? You here, like in machine learning, this would be like hyperparameters and a search across the hyperparameters, but here it's just, hey, you want X number of volatility or of variance in these rooms, and otherwise you'd have to do that manually, but randomness can just be boiled down to an integer here, and WorldForge and RoboMaker just take care of the rest, it seems.
Absolutely. So there you go. So we're just, the ones were just created. So you can see these are the 2-room variations. So you can see they were slightly different. The furnitures are a bit different in each one. So that's what you want that randomness, right? To be able to test. And then here is different variations. So I created some more for refresh it.
And Anabell, to be clear, because I haven't used this before, these are more than just pictures of the room, right? This is not just dynamically generated art. This is a full world, 3D world with all of the properties that someone could deploy a robotic application to in RoboMaker and perform the simulation directly in this.
Correct. I'm going to show you that in a moment, right?
Oh, okay. So I'm jumping
the
gun.
Just,
sorry.
That's all right. But yeah, this is like this is what we just created, right? Just by 2 clicks, right? We just created these worlds here. So now I'm going to switch regions just for the sake of this. What I'm going to do is just give you a bit more detail around these worlds, so we'll see them a bit better in this part. So I'm going to create a new world. I'm going to use the 1-bedroom apartment, and here, so this is where I want to sort of give you a bit more detail what it has. So you have a bedroom. It's got a living room, a bathroom, and a kitchen, right? So then, and you can customize the size of the rooms, the interiors, what the floorings look like, what the walls look like, and what furniture. Like you can see here, the furniture is dense furniture room type. So these things are important, right? Especially like flooring, for if it's carpet, does the robot get stuck in the carpet, or is it slipping on the tiles? Those things you want to test for, hence why you need the different types of materials in your worlds. So let's just say we've got this 1-bedroom apartment, but I'm going to need another bedroom because I need some space to work from home.
Don't we all?
So, so I'm going to add, say, bedroom 2, and I'm gonna say it's another of type bedroom. I'm gonna leave the areas as default. I'm gonna save it, but then I want to sort of make maybe some changes around the interiors of it. So this is the room I just created. I want to override the connection. So connection is like how the rooms are connected to each other, right? So I'm going to say add a connection, and I want to say that I want it with a doorway, and my bedroom is going to be connected to the living room, and save that.
So this is quite intricate. You know, I'm imagining if I were trying to do this outside of WorldForge, this would be the task of a designer or a 3D modeler to actually construct that in that way, unless they had built some sort of internal tool to even do that. But that sounds very difficult.
Absolutely. So that's definitely one of the reasons. And then the other part is like all this, I'm just going to create it. And because it has a type of a bedroom, it's going to put some bedroom furniture in there as well, right? So custom flooring, so you can choose different flooring types as well. So there's like, you can see some, like this is carpet, that's what you're seeing. So floorboards, you can see different types of samples of the floorboards. Let's just say we're going to use tiles for this room, and we're going to save it. So these are some of the changes, I guess, you can make when you're creating a world, and these are all customizable. And once you create it, so this creates a template, right? It's not the world. And from this, you can create different variations of it. So that's where I guess it becomes powerful. So let's go ahead and create this. Let's just create 2 of each, 2 variations and 2 floor plans. And while these worlds are being created, what I want to show you here is quickly that, so you know, if you wanted to try this yourself. So if you go to resources and just deploy the hello world, like literally click on that and create launch simulation job, that's going to give you a sample application. So with that sample application, I'm going to use that to drop my robot in this world that we just created. So that's
so for example, that sample application would be like the equivalent of whatever application I had built that would perform the behavior my robot would want, and that is what like the application is what I'm technically testing inside of the WorldForge's world.
Correct. So, so there's 2 concepts. There's the robot application and there's the simulation application. So in this scenario, we're going to use the simulation application.
Okay.
Yeah. So if you look at, so as because I've deployed it, so if you look at simulation application, this is what you see. And that, again, like since you can just deploy it from the console, but it's also open source. So under AWS Robotics, this is the open source application. So if you want to look at the code details of it, you can easily get access to it from there. So then if we look at our world, they're still generating, it's still running. So you can see the running job, and it's creating 4 different worlds.
So the reason why it's 4 would be because we had 2 different variables, and we chose 2 versions of each. So it would be the what is it, the word when you multiply 2 things, the product of the 2. That would be the resulting number of worlds.
Correct.
Cool.
There you go. And they're just created. So we just added, remember, if it was a 1-bedroom apartment, we added a bedroom, and we said we want 2 different variations and 2 different floor plans. So you can see the floor plan slightly different from the top and the bottom ones. You can see them slightly differently. And you can see the green is, again, where the robot gets dropped when you start that.
I'm waiting for the first apartment building to be built entirely by rooms generated in WorldForge. That'll be a fun one.
So now let's go ahead and create a sim job, right? Let's create a simulation job using one of these worlds that we just created. So in here, again, this is using the role that gets created as part of the Hello World deployment. Here we're going to choose melodic, which is one of the ROS distributions. And we're going to go next. And we're not going to use a robot application per se, because the default robot application in this just goes in circles. I want to control it just to show you the view from the robot. And here we're going to use the existing sim application, which is that hello world again. And so launch file is what you see here. That's the launch file. So there's a WorldForge launch file available as part of this sample application. And the package is just make sure. Hello world simulation. Great. And here we'll say import the world from WorldForge. So then you can go and browse your worlds, and these are the 4 worlds we just created. So let's pick one and choose the world. Next. Create the job. So this is creating a simulation job that we can then go in and have a look at, interact with it in Gazebo. I'll show you that in a minute. So while that job is being created, what I want to show is that these jobs, these worlds that you've created, what you can also do is, so you can choose the job and you can export it. When you export a job, it puts it in an S3 bucket. So you can choose your S3 bucket where you want it. And I need IAM role to do that and create. So the exporting, a lot of people use their own laptops for development, like I was mentioning. So you might run Gazebo, you're developing, you're doing unit testing on your laptop. So this world you've just created, you want to do some unit testing on your own machine. So this exporting it means that you can then get a copy of this world and use it in your Gazebo running on your own machine as well.
That's actually a good point that you brought up about folks doing maybe unit testing or trying to do development on their own machine. You know, anything graphical, I imagine, makes better use of your generation of these worlds. Maybe it would entail better performance with a GPU, let's say, but that often involves a more expensive device, right? So correct. I'm seeing here a world in which WorldForge, no pun intended, is enabling folks to now develop something that they otherwise would have been locked out of previously if they didn't want to invest or weren't able to invest in a device of that size. And with all the benefits of all of the on-demand nature of managed AWS services.
Absolutely, yeah. So you can see that's the job, that's the world we just created, and it's been exported as a zip file. So you can download that locally on your machine and run it against your code that you're developing locally and do your unit tests, etc. So by now, we should have, now we've got our simulation. So this is the simulation job we just created with our brand new world. So let's go and look at that. So as part of RoboMaker, what we provide is managed Gazebo. So this is Gazebo client, RViz and RQ2. These are some of the tools that robot developers use as part of their development cycle. So you've created your simulation and you can connect to it.
So similar to how I would, spin up a fresh instance and SSH into it, I can go directly into the simulation as it's happening.
Yes. So this is simulation as it's happening. So, and
I feel like this is this sounds quite familiar. I ended up wearing my Deep Racer shirt today. I don't know if the sleeve can show it, but with Deep Racer through RoboMaker, I believe you can also sort of take I'd say bird's eye view, but it is like car's eye view from the track and see what it sees inside of a simulation world. Yeah. So I'd imagine it would probably look something similar to this, right?
It would, because Deep Racer actually uses RoboMaker. So yeah.
It's all coming together. I'm like 5 for 5 today. I just can't miss. Yeah. Wonderful.
So this is the world we just created, and right in the middle there where you see the dot is where the robot is. That was the placement, the green cylinder that we saw. So that's where it got dropped in as part of this.
Hold on,
And,
I think there's a screen sharing issue. What we still see is your AWS console.
oh, really?
It may have come up in another window, maybe.
Yes.
If you drag the tab into this window, it should probably work as is. I don't know if that's possible.
Can I share all of it?
Oh, I see that third. Yeah, there we go. Awesome.
Okay. Yeah. So that's what we're seeing. So this is actually, so that's the world we just created. And the robot is dropped in the middle there. And then I guess I need to then show you the other part of it. So I'm going to open another tab, but I need to make sure to share that.
I think as you popped that one out, I don't know if the other browser. Oh, actually, no, we see that. Yeah.
Well,
it looks like it's loading right now, right?
Yeah, I want to see if I can just share the whole thing that way, because I need them side by side.
Yeah, desktop or desktop capture probably will work well for that. But I was going to say, so this is quite interesting because otherwise to explore these 3D worlds in this way, it looks like I would need to download maybe Gazebo or whatever this 3D modeling software is and open up the world inside of there to be able to then do that. But this is all directly in the browser through the console, right? I don't have to install any other software, right?
Correct. That's absolutely right. Yeah. So this is...
It's probably looking straight into a couch or something. Is that what we're...
So yeah. So can you see both of them now, or you're just seeing?
No,
one?
I can only see the one that shows the red texture. It looks like Sim48LFFKJ. Yeah. I think if you go to screen share and then do desktop share instead of window capture, it may improve that. But if we're trying to show both at the same time,
let me try it.
Yeah, no worries.
Nope.
We
not happening.
That's okay.
All right, so then I guess the other part of it is to be able to, you can steer the robot as well. So, but I guess the key. So now
there
you can
we go.
see.
So those were walls, and it was looking right at a wall before.
Yeah. So it's just going in circles at the moment, and it's looking at all the furniture around it, and
we want to move closer to that. Let's say we want to move closer to that corner over there by some of that furniture. Is that like throttle, let's say, or moment velocity in either the forward or back direction? I see meters per second. Yeah, it's bringing me back.
It's moving closer to it. Yeah.
Cool.
Now, Anabell, can we destroy this furniture with the robot?
Yeah, you can smash. Do you want me to smash into it? Is that what you're saying?
Yes, let's do it.
Full speed, just full gas.
There you go.
All right.
We're right. We're stuck behind it.
All right, 5 points.
I'm imagining a world where we have, we have Deep Racer. I know a lot of folks always enjoyed the show. What was it, BattleBots? Let's say. I'm waiting for a day where we have a BattleBots simulated competition, and seems like this would be maybe the precursor to making something like that possible. So I'll go out to the lab and see what trees I can shake and make that possible. But that sounds exciting.
I'll tell you, some sort of deal between AWS and BattleBots needs to happen.
Yeah. But this is, I guess, this is what we just created, and the robot is placed in it, and it can, I guess, move around. So this is where your application would run. So you would write an application to do, for example, object avoidance, right? Or to navigate through all of the floor plan, right? So those are the things that you would build in your application. And then when you run them in simulation, then you're able to see, to test, generate synthetic data, or validate your application. So make sure it doesn't, run into a cabinet or a wall or etc. Again, because they can be expensive. So
this is super interesting. I mean, I'm a huge gamer. I know Rob is as well, and in the video game space, a very tangible problem for players and for game studios is the ability to, let's say, make environments in a way where it's time efficient, where they've made a bunch of assets, but then they string them all together very manually. How do we not repeat that world, let's say? So like, how do we randomly generate sort of parts of the game that our players will go through? And this has been a problem and a challenge for video game producers for a very long time. I know we're very pointed here with the simulation space, but just trying to wrap my head around how far all of this technology has come to generate a randomized 3D worlds. It's fascinating.
Absolutely. I mean, so it's like I say, I studied robotics in the university, but that feels like ancient history these days. It's just what the things that how companies have evolved, how robotics has evolved since then. It's just amazing. I want to quickly show you the worlds we just created in the other region earlier. So these are all the worlds here when we went, the variations, but so you can see like there's 3 pages worth. So imagine we just did this in the space of this time. We created all these worlds in the space as I was showing you the other parts of it. And there's 3 pages of them, right? So, and you can create hundreds of these just by running a single API call or, a few clicks away, customize them, put some variations in them, and then create and run hundreds of simulations in parallel.
That's awesome.
It's also very interesting to me, the ability to also, I know there were a few checkboxes or parameters we could randomize across, but even starting location is something that sounds simple, but has immense value to randomize, right? Like, say for example, like the old DVD wallpaper, or the old like screensaver where the like little thing just like bounces off all the corners and such, right? Like if you start with the exact same location every single time for an app, for a given app that you're trying to test, you may never encounter a scenario where, let's say, the robot would end up in the corner, and then you've never tested that case, because you started with the same seed in every single one of your simulations. But by having different starting locations, you're essentially randomizing that seed. You are basically ensuring that your simulations are going to be more all-encompassing than otherwise. So that's really cool. It's a subtle thing, but it has a big impact in like the behavior of robots, because that could prevent, let's say, a build going out where everyone then reports like, yeah, this exact same weird behavior. Like when it's caught between 2 chair legs, it just doesn't know what to do, right? Like this randomization helps to curtail that early on in the build and the testing process. For sure.
Like the robot could say, your Roomba could be under the table somewhere. It might be stuck under a chair or a couch, right? So how do you test for that, right? So yeah, definitely it will help in those scenarios for sure. So I guess, that's all I wanted to show in this, is just how easy it is to create worlds and then be able to, I guess, export them and be able to run your unit testing on your own machines directly on the world you just created.
Well done.
Yeah, I know you said that's all you wanted to show, but the ability to spin up an innumerable number of virtual worlds with and you can string them together in all of these ways based on the pre-built templates with all of this randomization. That is nothing to scoff at. That is nothing to minimize. That is an immense problem and challenge that anyone working with robotics or trying to simulate is definitely jumping out of their seats to try and get their hands on right now. So
absolutely, yeah. But I guess we've made, I'm saying all, but I'm saying how easy we've made it, how easy WorldForge has made it for the QA engineers or the robotic application developers to do that. Absolutely.
Yeah.
Wonderful.
So, you want to leave us with any sort of how do people get started with RoboMaker? What are the resources and call to actions that we can share with the chat?
Yeah, I mean, just like you said, right? Go ahead, just run the Hello World application. Just go and start creating some worlds just to see how easy it is to do that. And just remember, you know, creating these 3D worlds used to be a lot harder, more expensive, and time consuming. You can do that easier, faster, and cheaper now, for sure.
Wonderful. And you know, there are a few things I would love to see in WorldForge. Like if I could get a giant robot in there, that would be really cool. I could think of a bunch of different things, but if folks have a particular object that they would like to see supported directly in WorldForge, is there a way for them to let you know?
Absolutely. So like I mentioned earlier, like this is the start, right? So we want our customers to tell us what they want, and you know, that's how we build our services. So please contact us, let us know your use cases, and we're more than happy to work on that, for sure.
I just realized how silly the idea of using of mentioning a giant robot in RoboMaker, which is designed for robots, but you get what I mean, right? If I wanted the Eiffel Tower, let's say, as or the Statue of Liberty as a giant model inside, maybe that would sound a little more fitting. But yeah, cool. Well, yeah, we will get that that email address thrown out in chat. So, you know, again,
awesome.
Here on the What's Next show, we love being able to surface the service teams that build these things, connect them with the community. It goes both ways, right? Sure. So wonderful. Well, I'm sure we have some links. We could also, yeah, we have those in chat. Cool. Well, this was building 3D worlds in with WorldForge in minutes. Very exciting stuff. Man, I'm trying to think. Is there anything else? I can't think of much. I mean, again, it's all in the console, right? You don't have to leave.
All in the console.
No other software. And
yeah, I mean, the thing is, like, if you want to build your own robot application, then you can either use the development environment in RoboMaker or use your own laptop to build your own robot application, and then drop that in, use that as the app in your world that you create. Yeah.
Wonderful. Well, I think we're approaching on time here for this session, but Anabell, I wanted to say thank you. This was really great. I don't get too much of an opportunity to dive into RoboMaker personally outside of some of the deep racer stuff that I do, but this new launch in WorldForge is very, very exciting. I know any of the customers already working with RoboMaker are going to be quite excited about it. So
absolutely.
Yeah, thank you again. Yeah. Awesome demo.
Thank you. Thanks for having me. Thank you.
Thanks, Anabell. It's been a pleasure and a privilege.
Awesome. Well, everyone in the audience on Twitch and LinkedIn Live, stick around. We have one very quick closing segment that we will do, and we will be right back in just a moment to do that. So hang tight. We'll see you soon. We are back. Some familiar faces here. Nick and Rob, hosts of AWS What's Next. Hopefully you knew who we were, given that we've been here for about 2 hours and 10 episodes, cumulatively tens of hours at this point across the past few months. But again, some exciting launches. We say every episode is special, and I always feel silly saying that in a way, and then I always am faced with some of the launches like what we showed today, and they're just unlike anything we've shown on the show thus far, right? We are always impressed by the breadth of what is covered here on the What's Next show, but broadly the services that AWS creates.
Yeah, absolutely. I almost forgot that it was the 10th episode. Time really flies, especially in this strange time that we're living in now. But is this the first episode where you've not said the term Come on, Nick.
But I mean, it's not fair, right? Because it's like the Fermi uncertainty principle, right? It's like if you tell me you're gonna measure it, it affects the actual
Yeah, I know,
phenomena you're trying to measure,
I
right?
I'm
So
hoping you.
if there was a way for you to whisper to the audience, like Nick's gonna say undifferentiated heavy lifting, and then it would have been, you know.
I know.
But I'll forget by next episode because
Let
my
the cat out of
memory
the
is not
bag.
great.
And then we'll have some fun with it.
Exactly. But
you want to describe this the Iron Code segment that we do here?
Iron Code, Iron Chef, what have you. We take some of the launches that we had covered in today's segment, and we imagine if you had to cook a dinner with those surprise ingredients, or in this case, you had to string together a bunch of these in an application that made great use of them, what would that look like? And usually we have 3. Today we have 2, so it's sort of just a pairwise interaction. I feel bad, but I don't want to take more credit than credit is due, because Anabell actually had a great example when we were on the holding screen before we got onto her segment. But actually, I don't know if you heard it. I heard it, so I don't want to go first. I'm going to pass it to you. If you had to string together both Bracket, Amazon, a managed service for quantum computing, and RoboMaker WorldForge, how would you string those together, Rob?
Well, before I take a crack at it, I want chat to get in on this. All right. So remember, chat, the prompt is, if you were to combine Bracket and RoboMaker WorldForge, what would you build with the combination of those 2 things on AWS? And the crazier the idea, the better. So we want to hear your answers in chat. And while you're thinking about that, let me take a stab at it. Okay, let's see. So we've got quantum computing with simulation as well as real hardware underneath. We've got RoboMaker WorldForge that can generate 3D worlds for you. Test out your robots. I don't know. That's hard.
I mean,
that's hard.
It's actually interesting because I think there's like this like transitive property. If do you mind if I give a little hint?
Yeah, go for it. I mean,
there's no right answer here, obviously, but there's no wrong answers either. It's you can build whatever you want. The rules are made up. Points don't matter, right? As the saying goes. Back when we were talking about quantum computing, oftentimes those involve simulations to begin with, right? Those are the classes of problems that Bracket would help to solve. And so when we have RoboMaker WorldForge helping to run simulations, I'm imagining a world where we have we could have, instead of qubits, we have like quantum entities in our world, right? They are simultaneously in multiple places at the same time. I don't know, it's getting a little meta, getting a little ridiculous, but
yeah, I mean, I guess my very, very shallow understanding of quantum computing from that excellent crash course we got from Martin. I mean, he was saying that the thing about quantum computing is that you kind of need to design the algorithms in a way that lend themselves to quantum analysis, right? So I wonder, I mean, what we're really trying to do with RoboMaker, if you apply it to something like iRobot and Roomba, is the ability to detect good or bad behavior of the robot in any number of environments, right? So, I mean, really spitballing here, but maybe it's a matter of, if you can kind of simulate all of those in parallel and find the one, like magically hone in on the one out of 10 million simulations. Because the thing is, like, those variations start to really add up, right? The couch is here, the living room is there, and...
Well, I was also going to say, like, we learned about, like, qubits, like, that phenomena can't even be necessarily modeled in a single qubit, right? Like the couch being in a certain location, like we're talking like a computationally explosive sort of system here. So it sounds very difficult, but something that we can punt over to the research side and the engineering side on some of the the computer
here's
providers.
one. I mean, this one is a pretty tiny corner case. Well, hear me out. But because the quantum computers can kind of introduce really, I mean, we saw that how the quantum computers differ from the classical computers in that you can make general predictions about the distribution of what the what the outcomes are going to be, but there's always going to be some sort of noise involved. Right? So maybe we can use that as a source of generating random noise for the environments for RoboMaker WorldForge, and whether that's in kind of like the image intake into the the operating system, or whether that's variations in the environment. That's the kind of thing that a robot is going to have to deal with, ambiguities, like crazy lighting conditions, or furniture it's never seen before, or the combination of like a carpet and so yeah.
I was going to say, in a way, WorldForge could be the, Martin showed us in bracket, there's this simulation with the APIs that still run on a classical computer, and then you have the quantum simulation. Maybe in a way, for certain robotic scenarios, WorldForge is the simulation layer, or the simulation on classical computing, and then there are other problems in the robotics testing space that could be inherently quantum. Right. Yeah. And then quantum, bracket is used on those quantum computing providers on the back end to be able to then solve that. So maybe it's not necessarily that they string directly together, but they are two parts of this same sort of fluid robotics build, test, deploy, simulate, which is in the testing phase of this. So
okay, I know.
Okay.
All right. I'm going to build a startup called Quantum Robotics, just because that sounds cool. I don't know how I'm going to combine these things. I mean, I might make an API call here and there between the two, but whatever. It doesn't matter. The point is that Quantum Robotics will put this in front of VCs and people will throw money at me.
All right. So you've got a pile of money, right? What do you do next?
I don't know.
Well,
doesn't matter.
That's a question for another day, it seems. But without further ado, we only have those two to string together. I think we've taken a adequate crack at it here.
Swing and a miss.
Swing and a miss. Yeah. All right. 5 for 6. Okay. I'm all right today. I'll take that as the batting average. But if you're new to the channel, thank you for joining us. We hope you enjoyed. We simulcast live to both Twitch and LinkedIn. But if you're looking to watch more content like this, the easiest way to do so is to actually follow along on our Twitch channel. So twitch.tv/AWS. If you're interested in really bad jokes and me tweeting about when we'll be live, you can also follow myself and Rob. Here we have the links in chat. Our Twitter handles are on the screen. We try to tweet and let everyone know before we go live. But typically we stay on a pretty consistent schedule. We try to stream every 2 weeks at about noon Pacific, 3 p.m. Eastern, barring any gremlins running around in our production hardware, aka me. Not having my graphics drivers updated at times.
But that's my problem typically, right?
No, that's the that's the gremlins running around inside of your webcam cable that mess things up.
Nick, did you know that simulcast is my second most favorite portmanteau?
After undifferentiated heavy lifting?
No, that's not. Come on. My favorite one is Chris Sandwich.
Chris Sandwich. Croissant sandwich?
Yeah.
Over cronut?
Oh, that's a good one too.
Okay, I mean, even RoboMaker in theory, RoboMaker is one, right? I mean, you just chop up. Yeah. So
that's true. All right, we'll have to settle this on the next episode. A good reason to tune back in. We'll figure this out next time. But everybody who stayed with us to the end, thank you so much. We'll look forward to seeing you on episode 11 on September 4th.
Double Hockey Sticks airing live at noon Pacific, 3 p.m. Eastern, August 4th, right here on twitch.tv/AWS and on LinkedIn as well. Thank you again to everyone who tuned in. Thank you for the participation in chat. Thank you to all of our guests. Thank you to the service team members that were in chat answering questions very diligently. That definitely does not go unnoticed. Congratulations again to all of our newest AWS heroes. We appreciate you greatly. Thank you again for tuning in, everybody. We'll see you in 2 weeks on the 4th. Have a great weekend.
Bye, everyone.